Welcome! Today, we're going to dive into a chemical puzzle that at first glance seems totally impossible. How can you take the exact same set of atomic building blocks and end up with completely different molecules? Let's figure this out. Yeah, I know what you're thinking. It doesn't really make sense, right? You'd think the same ingredients would always give you the same result. But, in the world of chemistry, and especially when we're talking about our star player, carbon, the blueprint is everything. How those atoms are connected changes the whole game. So, to really get a handle on this puzzle, we first need to get to know our main character, the element carbon. It's the foundation of life, it's in the fuel we use, and it has this one very special superpower that makes all this incredible variety possible. And that superpower has a pretty cool name, catenation. It sounds a bit fancy, but all it really means is that carbon is unbelievably good at linking up with other carbon atoms. It can form these long, super stable chains, branched chains, even rings. This is what makes it the ultimate molecular Lego piece, It can build a practically infinite number of different things. Okay, so that's the theory. But let's actually see this in action. We're going to solve a little something called the butane puzzle. Let's build it from the ground up, piece by piece. So here are our building blocks. We've got 4 carbon atoms and 10 hydrogen atoms. That's it. That is the entire recipe. Seems simple enough, doesn't it? So with this simple formula, C4H10, here's the big question. Is there only one way to snap these pieces together? Or does this puzzle have more than one solution? What do you think? Well, let's start by just connecting our 4 carbon atoms. We'll build what chemists call the carbon skeleton. And check this out. Right away, we find 2 different possibilities. We can either link them all up in a straight line, one after another, or we can make one of them branch off the middle. 2 totally distinct blueprints, right from the get-out. All right, time to finish the job. We're going to take those 10 hydrogen atoms and add them to each of our carbon skeletons to complete the molecules. So what happens when we do that? And there it is, the big reveal. We've just made 2 completely different molecules. They have their own unique shapes, their own structures, but, and this is the absolute key, they are both built from the exact same 14 atoms. And just like that, we've solved the puzzle. So over on the left, we've got this straight, unbranched chain. That one's called N-butane. Then on the right, you see that more compact, branched structure? That one's isobutane. 2 completely different things, but they share the exact same formula, C4H10. And this brings us to a really important idea in chemistry. These 2 molecules are called structural isomers. That's the official name for it. It's when you have compounds with the identical molecular formula, but a totally different arrangement of atoms. Okay, so they look a little different on paper, but you're probably asking, so what? Why does any of this actually matter? Well, this is where it gets really, really cool, because that structure, it's everything. A seemingly tiny difference in the layout can have huge real-world consequences. And believe me, this isn't just some one-off trick with butane. The possibilities just multiply like crazy. If you add just 1 more carbon atom to make pentane, you suddenly jump from 2 possible isomers to 3. And as you keep adding more carbons, the number of possible structures just explodes. This is how carbon is able to build the incredible diversity of molecules we see all around us in nature. It really all boils down to this one simple idea. The difference lies in the manner in which the carbon atoms are bonded to one another. It's not about what you have, it's about how you put it together. Some of the most profound differences in our world come down to these simple changes in how atoms are connected. And if you want the ultimate proof, just look at diamond and graphite. Think about this. Both are 100% pure carbon, nothing else. Yet one is the hardest substance we know, and the other is so soft it literally flakes off onto a piece of paper when you write with a pencil. The only difference, their structure. A rigid 3D lattice versus these slippery, flat layers. Same atoms, completely different worlds. It's amazing. So here it is, the fundamental takeaway from all of this. The way atoms are arranged defines everything about a substance. Small changes in structure lead to huge changes in properties. It's a core principle that governs everything, from the fuel in a lighter to the very DNA that makes you who you are. This simple idea, this concept of structural isomers, it really just unlocks a whole universe of possibilities. It's the secret behind the mind-boggling variety of life and materials that we see all around us. Which kind of leaves us with one final fascinating question, doesn't it? If changing the position of just one atom can change everything, what else is possible out there?